are going to continue with our program, and today's the last day of the Ophase, sadly. And we're going to start into the day with a scientific talk by Professor Ullmann, who will introduce himself probably now first.
Thank you very much for the introduction. Glad to see you all here. Thanks for the invitation. I will talk, whoever knows me knows what I'm going to talk about, analog computing, of course, because there's nothing more interesting than analog computing, at least in my mind. And I'm not only sure that analog computing will gain an important place in the scientific and commercial world in the near future, I now also have data to substantiate this. So what is analog computing and why should we care? Everyone has heard about quantum computing, but I think most people only have a very fuzzy idea of what a quantum computer might be. Adiabatic quantum computers, quantum gate computers, whatever. And quantum computers can also be categorized as an analog computer because they work by using a model, a physical model, to solve a problem. So if you want to solve an optimization problem, you could, for example, resort to an adiabatic quantum computer from D-Wave or some funny machine like this. And basically, you implement a quantum mechanical model of your mathematical problem you want to solve, and that makes a quantum computer basically an analog computer. However, I'm not that interested in quantum physics. It's too complicated. I don't understand it. But what I understand is analog electronics, and that is another approach to doing computation. Why not use simple physical processes, for example, like Kirchhoff's law that you, I hope, all remember, the currents flowing into a junction must sum up to zero. Sum up, wow, I can sum by just adding currents. I can actually use currents to implement an addition operation. I could, for example, charge a capacitor and solve an integral without any numerical scheme. I can use very simple physical properties of electronic circuits to solve intricate mathematical problems. And the big advantage of this is that we can avoid most of the problems of our classical digital computers. We all have digital computers and we all know about their inherent problems. The power consumption is horrible. I still laugh about Elon Musk's mega hard computer centers. I really love the pun because I really hate Microsoft. But honestly, a computer center that is planned to consume up to 1 gigawatt of power, that is incredibly cool, and I would be the first one building a nuclear power plant just for the computer center, but it does not scale. That is obviously not an option, and I doubt that outer space might be a solution for energy intensive digital computer centers. So high power consumption will eventually break our necks. Our clock frequency, it's horrible. We are stuck at about 3 gigahertz. We are stuck at 3 gigahertz for more than 20 years. Nothing has changed. Why? Because energy consumption scales about quadratically with clock frequency. So just doubling your clock frequency would quadruple your energy requirements. That does not scale. Then our on-chip structures, there is not much room to further shrink things down. Okay, you have FinFETs and you have 2 nanometer technology nodes, but below a few hundred picometers, there are not enough atoms left to actually build anything from this. If you have ever tried to actually use a parallel computer, you know that parallel computing is hard. Amdahl's law will also bite you eventually. And eventually, if you have a look at the actual silicon real estate, you will realize only a very small portion of the silicon on our CPU chips is actually involved in computations. Most of the silicon real estate is spent for caches, for control logic, for register renaming, out of order execute, whatever, you name it. It is a mess. It's really incredibly messy how our current CPUs look like. And if you think about supercomputers, you think about this. This picture changes regularly depending on the top 500 list. And I've in the meantime seen one of these systems. The blue and red things are not wires. These are tubes for cooling liquid. And one of these racks consumes 0.5 megawatt of power. One of these blades is 15 kV. That is impressive, but does not scale. And when you look one floor below, you see all the equipment required to get rid of the excess heat, which also does not scale at all. And the reason for the high power consumption of digital computers is obviously that we have resorted to represent our values as binary values, zeros and ones. That seems very plausible and elegant at first glance, but the problem is you have to switch transistors from the on to the off state billions of times, billions of times per second, and billions of transistors per chip. So eventually this looks like a short circuit from a DC point of view, because at the moment of switching, both transistors will conduct for a very short time. But the main problem is the parasitic capacitance, CL. You have to discharge and recharge and discharge and recharge billions of parasitic capacitances on your chip, and that basically is the main driver of your power consumption. And you can't get rid of this unless you get rid of the representation of values by binary values. And of course you could get rid of this. I'm not making this up. I actually saw this. That is one of the advertising attempts by HPE, HP Enterprise Solutions. They honestly advertise their system with, look, we can heat a bathtub with the output of fractions of one of these blades. But that shows how incredible the problem of getting rid of the excess heat in modern digital computers is. Something which currently pops up again is liquid immersion cooling, and everyone goes nuts and wow, that's so new. No, it isn't. It's very old stuff. We already had this back in the 80s with the Cray 2, for example, that was immersed in a Freon tank, which looked absolutely gorgeous, but was a nightmare to repair and maintain this machine. When you had to swap a module, you had to drain a ton of liquid Freon. You had to remove your module, you had to install another one, you had to refill your tank, you had to bubble out the free. It was really nightmare, and it will be a nightmare, and that is not the solution. We have to look into different computational paradigms to get rid of our current digital machines, at least for certain classes of problems, to get our energy consumption down. And here we see the historic development of clock frequencies. When I started computing, don't laugh, that was here. My machine had roughly 4 megahertz clock frequency. And it got warm to the touch, but didn't need any active cooling. There wasn't even a fan, there wasn't even a hole in the enclosure. It just got a little bit warm. And you see the clock frequency raised exponentially. But since about 2000, we are stuck at around about 3 gigahertz, mainly due to the energy barrier. We can't get rid of the excess heat, and we can't justify the additional energy requirements for higher clock frequencies. And when we have a look at a classic, I know Core i9 is not the most recent one, but it's a good example. If you have a look at how the silicon real estate is actually used, you will see a large portion is just the shared third level cache. And then you have a large portion that is uncore, counters and bus interfaces and whatnot. Then you have your performance cores and your efficiency cores. And if you could zoom in further, you would realize that within the performance and efficiency cores, you only have a few, maybe 5 or a dozen arithmetic logic units per core. All the rest of the electronics here is just used for data management, transferring data from memory through an arithmetic logic unit back to some memory, controlling the out-of-order execution, controlling register renaming, all the horrible things we need to speed up our CPUs. So what would happen if we would use all of our transistor functions to actually do compute and not just store data? What if we could use 100 billion transistors to build a computer and not a big memory system with a small bottleneck that funnels all data through a handful of arithmetic logic units? And that is the basic idea of an analog computer. Here you see, you all have seen diagrams like these. You see the internal structure of a processor like this, and you see you have a first level instruction and data cache. You have control systems, instruction decode queues, allocate, rename, retire. Wow. Basically, I'm more than amazed that it actually works. if you try to understand what a CPU does, it's basically impossible nowadays. Back in my days, long, long ago, you could hook up a logic analyzer and just look what does it do. But nowadays you have no idea what it does because it does everything out of order, and the sequence with which it reads something out of memory is no longer the sequence in which it will execute instructions. Let's have a look at a few numbers. Currently, the top 500 list is known by all of you, I think. Back in the 90s, we were eagerly waiting for the top 500 list twice a year. Basically, like other people were waiting for the Playboy of the month or something like that, and we were all dreaming, oh, what could we do if we had such a machine? And we came up with all kind of crazy and nut problems that we would like to solve. But nowadays, the fastest system, at least according to the top 500, which has a certain underlying benchmark, is El Capitan in the USA at the Lawrence Livermore National Laboratory. These are the guys who build nuclear weapons, for example. And this system has 1,809 petaflops, which is pretty incredible. 11 million and something cores, have fun programming that. About 30 megawatts of power consumption without the surrounding equipment. So there's not the air conditioning and the cooling systems included and the like. And you get about, and that is a very impressive number, about 61 gigaflops per watt. On the other hand, you have a human brain, and the human brain is estimated to have a computational power of about 38 petaflops. And the human brain, in my case, works from vegetarian food, basically nothing, and delivers 38 petaflops at 25 watts, day and night. 25 watts. The computational capability of a brain is 1.52 petaflops per watt. Not mere gigaflops, but petaflops per watt. And the trick of the human brain is it's not an algorithmic machine. Your brain does not execute a program. If it did, you wouldn't function. You couldn't talk and stand or talk and walk. You would be hopelessly underpowered for anything required for survival. What your brain does is, your brain is an analog computer. Your brain consists of billions of computing elements, neurons, and these neurons are interconnected in a certain way, making your brain and my brain, my brain. And why don't we do this in the electronic domain as well? Why don't we build electronic circuits consisting only of computing elements to solve intricate problems instead of going the algorithmic way over and over again? And that is all what analog computing is about. So algorithms have a lot of problems. You are all used to algorithms and you think it's a holy grail. It is not. There's a reason why basically nothing in nature executes an algorithm, because nothing in nature has the energy budget that would be required for an algorithmic solution. And reality is 100% parallel. And a biological brain is a perfect example for a non-algorithmic supercomputer. And our current computers should better be called stored program computers, because we execute instructions read from some memory. And on the other hand, we have analog computers and quantum computers. Let's have a look at what an analog computer is. An analog computer, the word comes from the Greek analogon. It means model. The idea is I build an electronic model for a mathematical problem that I want to solve. An analog computer is incredibly energy efficient. We have in the lab now, we had our second tape out. Tape out is when you have designed your own silicon and you get your first specimen from the fab back that you can put through their paces in your lab. And we can demonstrate that we can solve certain intricate problems several decades faster than on a digital computer, and equally much more energy efficiently than on a digital computer. In a digital computer, you are used to represent values as bits, 32 bits, 64 bits, whatever, or FP4 if you are from the AI community. I still think FP4 floating point with 4 bits is completely nuts, but obviously it works. And what still baffles me is that it's not even symmetric around 0, but not the topic of today. But why don't we represent values, for example, with a voltage? Why don't I represent the value 1 with 1 volt and the value 2 with 2 volts? And using a few resistors and a few transistors, I could, for example, add 1 volt plus 2 volts equals 3 volts. That's basic analog circuitry. And I get for basically free a computing element that can add values. And if I have a lot of computing elements, I not only need summation, I also need integration, which is basically the magic operation of an analog computer. I need multiplication, I need functions, I need basically all the operators you are used from mathematics. But when I have black boxes built from electronic components that implement each black box, then I can solve problems by just letting physics solve the problem. One of my colleagues once said, and I really love this idea, we give problems an electronic domain in which they solve themselves. And that is just beautiful. It's philosophical and it's beautiful because there is no program. I build a circuit and the circuit gets initial conditions and I then watch the circuit to reach some steady state or some non-steady state depending on what I want to see. And if we have a look around our world, is analog from the value perspective as well as from the modeling perspective. Analog computers are not general purpose machines. I don't, bless you, I don't advocate to get rid of digital computers, although I could throw them out of the window at least twice a day nowadays. The older I get, the more I hate these machines, especially modern software. Modern software just sucks on so many levels. I can't express it without using swear words. But what I advocate is to add coprocessors to our digital computers. One coprocessor will sometime in the future be a quantum computer, but we will also need an analog computer as a coprocessor. Nowadays we are using graphic cards, headless graphic cards, basically for doing all stuff with linear algebra in the AI area, but we will also see analog and quantum coprocessors to speed up certain problem domains. Let's have a look how an analog computer looks like. And I brought an analog computer with me, a very tiny one for educational purposes. That is a real-world analog computer. That's affectionately called the analog thing. And it consists of a number of computing elements. You have, for example, 5 integrators, you have 2 multipliers, you have 4 summers, you have 4 inverters, and you have 8 coefficients. These are the potentiometer knobs below my hand. And that is enough computational power to implement really interesting systems and to solve certain systems faster than in a modern digital computer with basically trivial analog electronics. I'm not advocating going towards machines like this. You see, programming a classic analog computer like this is a very manual process. You have to actually wire it. You wire your program. If you now think, oh, looks like an FPGA, yes, exactly. And that is exactly what we and other researchers are currently doing, bringing all this on integrated circuits with crossbar switches so that we can get rid of these nasty wires that have to be plugged in. But the idea remains the same. We have individual computing elements which we connect with each other to implement a certain mathematical problem, and then we just let physics solve the problem. This, for example, is a certain chaotic system that I implemented over the Easter holidays. And it is a nasty, chaotic system which requires a clever numerical integration scheme to get a reasonable solution on a digital computer, because simple integration schemes will just diverge. On the analog computer, it works like a charm because I let just physics solve the physics problem. That is basically natural. So an analog computer consists of a number of computing elements, basically only computing elements. There is no need for memory. There is no need for a control logic. You have just computing elements that are interconnected with each other. So an analog computer program is nothing else than a directed graph. The graph represents which element is connected to which other element. And the charming thing about this is all your computing elements work in complete parallelism. There is no von Neumann bottleneck. There are no mutexes, semaphores, no NUMAs, non-uniform memory architecture. All the problems we have learned to basically accept and sometimes even cherish in the digital domain are gone because there's no memory, there's no algorithm, there's just structure in an analog computer. I really came to dislike the notion of analog computing because most people think, oh, analog computing, that sounds boring and old-fashioned. And nothing could be further from the truth. The problem is people don't think about the Greek word analogon for making a model, they think of a record player or something boring. Sometimes people who have no clue about whatever. I was asked not too long ago by someone, oh, so you're using relays like Konrad Zuse? Oh, no, that was digital, and oh, no, on so many levels, no. I personally would prefer to recoin this term to natural computing or physical computing, because that is what it actually does. We let physics solve intricate problems. Let's have a look at a very simple, boring example. We want to compute something like A times B plus C. And you can think about basically any high-level language where you can just write A times parenthesis B plus C parenthesis. If you program in COBOL, which I hope you don't, you could write horrible things like add B to C, giving D on overflow perform panic dot. That would be a valid COBOL statement, but that's just horrible, just to remind you of horrible ancient languages. But if you do it on an actual machine in something like assembler code, to solve this problem, you need 3 loads. You need to get your values A, B, and C. You have 2 operations. You have to add, you have to multiply, and you have to store your value. That is 6 instructions that you have to execute. And if you only had this single thread, there's not much overlap that you can exploit. If you have multi-threading, okay, you can throw in instructions from different threads, but basically you have 6 instructions and they all depend on each other. You could throw the 3 loads in a load pipeline, but then you have to wait for the first value to arrive, and you need the result of the addition operation, the multiplication operation. Good luck, because everything is pipelined and you have to wait for ages to have the add instruction finished. It's incredibly complicated nowadays. In an analog computer, you need just 2 black boxes, a summer and a multiplier, and you connect them with wires, and every line is an actual wire. In the case of this analog thing, it would be really an actual wire connecting a summer and a multiplier, and value are then represented with voltages or currents, for example. And that is just a brilliant idea. I have no memory, I have no algorithm, I just input some voltages or currents and I get a result out as quickly as physics allows. Of course, this program is way too simple to show anything about analog computers. And of course, you know that there's no free lunch theorem in computer science. Analog computing also has its drawbacks. Precision is pretty limited. You get about 3 to 4 decimal places, so 10 to 12 bits of precision. And many people say, oh, what do we want with 10 to 12 bits? That's enough for most of the problems. And if you are thinking about artificial intelligence, when a floating point 4-bit number suffices, then 10 bits is more than sufficient. When you do integrations, you only have time to integrate to, so your only free variable is time. That is nasty if you have to solve partial differential equations, but there are clever solutions around this as well. And interestingly, generating arbitrary functions is not trivial on an analog computer, but on the other hand, I also brought something else to show you with me. Imagine you have to implement a logarithm function on a digital computer. How would you do it? How would you actually write a function log? Log gets a double, returns a double, and the first idea you come up with is, I think, a Taylor polynomial, probably. You would write down the Taylor polynomial for the log function, and then you would imply something like the Horner scheme to evaluate the shit. We have somehow lost that we just wanted to implement a logarithm function. We are stuck in loops and multiplications and additions and mumbo jumbo that has nothing to do with the actual problem of implement a logarithm function. And I've brought an ancient logarithm function from 1959 with me. May I present? That's a log. And the interesting thing, there's not even a single transistor on this printed circuit board. That's just a bunch of resistors and diodes. And that is all that you need to implement a really, really good logarithm function. And that is the charming thing about analog computers. Things that are really difficult and hard in the digital domain get sometimes incredibly simple on an analog computer. Just use a few diodes with appropriate bias currents and use these diodes to implement a certain function that you want to use in your program. So a single plug-in card like this could implement a sine, a cosine, a log, whatever you need. because I let physics solve the problem. So an analog computer may form the basis of what is called a hybrid computer, basically a tight coupled system consisting of an analog computer as a coprocessor and a classic digital computer as the main machine. So the analog computer will offload the digital machine from compute-intensive tasks. So ideally, when we manage, and we have managed to get rid of the cables and get to reconfigurable analog computers, we can also task the digital computers with, dear digital computer, I have this problem, could you please configure my analog computer on chip accordingly so that it will solve the problem. So the digital computer will reconfigure the analog computer, will then give the analog computer a start signal, start integrating, wait for a moment and read out the solution of the problem. And that is basically the holy grail. I have a specialized machine, the analog computer, that is ideally suited for everything which involves dynamical systems. Every system that you can describe with coupled differential or partial differential equations is ideal computational fodder for an analog computer. Let's have a look at possible application areas. Basically, there are incredibly many application areas. The area I'm most interested in is just classic high-performance computing. But I think the commercially most viable application area will be artificial intelligence. Apart from that, I'm not happy with what is currently going on with artificial intelligence. Not that I'm afraid that it will exterminate humanity or the like, but we are doing it wrong. And I would be the first one to help the robot apocalypse with WD-40 if they are in need, because I really hope for machines to take over one day. But we are doing it wrong. We are doing it with linear algebra. I bet your brain does not do linear algebra. Why? Why are neurons so horribly complicated? When you have a look at an actual biological neuron, ideally from a textbook, not from a living specimen, being a vegetarian, I despise these methods, you will realize that an actual neuron is incredibly complicated. It spikes, it bursts, it needs time to recover from a spike or from a burst. And I'm pretty sure there's a reason why they are complicated. Nature had millions, billions of years to basically optimize these systems. And I'm really sure there is a reason why neurons do more than just implementing a scalar product and an activation function. That is way too simple. We will be stuck at a certain point with our current approach to artificial intelligence. And I'm sure that actual artificial intelligence eventually will have to go the analog route down because just of power efficiency and the possibility to implement reasonably realistic artificial neurons. Then you have a bunch of medical applications. I can basically guarantee most of you will reach 100 years of age. And I can also guarantee you it won't be fun. Definitely not. You will need nasty medical devices to live a life-worthy life, I hope. Pacemakers and brain pacemakers and whatnot, and insulin pumps and sensors. And nowadays, these are all pretty clumsy devices. But imagine you have a technology like analog computing that is so energy efficient that you can basically build implants that live from and with the body of the patient. They generate their energy by energy harvesting, and they can seamlessly adapt to the biosignals from your body and inject biosignals. Then you have industrial control systems which were analog and then were replaced by digital because digital is so much simpler and oh shit, our critical infrastructure is pretty hackable. Maybe it wasn't that good of an idea to go all digital industrial control systems. Then you have signal pre and post processing. 30 to 40% of the integrated circuit functions in a modern smart device are analog functions. You have to interact with audio, with microphones, with speakers, with a screen, with touch screen, with whatnot. That's all analog. You can do trigger word detection. You don't have to actually understand sentences for many applications, but for a smart and always on device, you need just something that can wake up based on some auditory signal. You can do Monte Carlo simulations, you can solve optimization. Basically, you can do basically everything with an analog computer as long as you can describe your problem in the form of differential equations. And that is basically what makes nature, nature. let's have a look at a short history of analog computing. And I emphasize short because I could deliver at least a 2-semester lecture on this topic alone. The history of analog computers is even richer than the history of digital computers. The first known analog computer is more than 2,000 years old, the mechanism of Antikythera. And we are still figuring out incredible details and functions of this mechanism. It's a mechanical analog computer, and it basically implements celestial mechanics. If there was ever something where one could say it looks like alien technology, it's that specimen. It's still not clear who made it. It's definitely not clear how it was made, because it exceeds what one thought possible for this time. And it's also not clear how the heck did they figure out the math that is underlying. For example, for the lunar trajectory, there are perturbation terms that weren't known for the next 1,500 years. No idea how they did it, but that was the first analog computer. That was a mechanical model for complex celestial mechanics. Then much time went by and nothing happened. I really wonder what the people did. Heron von Alexandria implemented the steam turbine basically, and then we had the Dark Ages and religions and whatnot, and it took 2,000 years before we went to the moon. Could have been a little bit faster, in my opinion. In the 1870s, Lord Kelvin, famous Lord Kelvin, was interested in predicting tides. When you think about merchant ships, sailing ships, you have to know when you have an incoming or an outgoing tide, because ideally you let your sailing ship being pulled in by the tide into your harbor. And it was clear that you can synthesize a tidal function by a Fourier synthesis. Have fun doing this manually, adding nasty sine and cosine terms. But doing it mechanically is pretty simple. You see these tiny circular things that are arranged in this V shape. These are sine and cosine function generators. These are basically pulleys which are mounted eccentrically. And the addition of these terms is done by a little steel ribbon that is wound around all of these sine and cosine function generators. And with the hand crank, you let time run, and this controls the position of a pen, and it basically draws the function of your tides at a certain harbor for which you know the tidal elements. That was a brilliant development, and we had such mechanical tide predictors in use well into the 1970s. Even in the 1970s, mechanical contraptions like this could outperform every digital computer for a certain problem, in this case, Fourier synthesis. Then war, as so often, the father of many things. Imagine you are on a ship and you want to shoot another ship. That is a nasty problem. Your ship is moving, your enemy ship is moving, everything is moving in 3 dimensions, and you have a torpedo going from A to B, and when it reaches B, the enemy ship is no longer at B, and that's a mess. So you have to do predictions. You have to predict where will the enemy ship be, how will the torpedo be deflected while it runs through water to actually hit your enemy ship. And that is an incredibly nasty mathematical problem that was mechanized in this mechanical analog computer. Then you had actual analog computers for peaceful purposes, and I like this because it shows how difficult it was back then. You have your computing elements here, that's for example an integrator, and the mess of axles and gears in the middle, that's your program. Reprogramming this thing could take up to 2 weeks because you had to dismantle it completely, and then you ended up with a big Tinker toy set for grown-ups with hundreds and thousands of axles and gears. However, it was much more efficient than solving certain problems manually. Then war again, try to steer a rocket from point A to B. That's not trivial. Just to stabilize the rocket, that was the birth of the analog onboard computer for the German A4 rocket. And that also gave birth to the first analog rocket simulator in the 1940s. When the US captured this machine, they used it until 1955 for actual work at NACA and then NASA for the development of the Hermes system. And you had other peaceful applications also in the United States. In this case, that was a chemical power plant simulator, simulate reaction kinetics in faster than real time, for example. This particular machine was called Polyphem or Polyphemus due to the single oscilloscope tube, which looked like the singular eye of the Cyclops Polyphem. And this implemented reaction kinetics for chemical industries. Then you had, that is a nice picture because it combines two things I'm very interested in. You see Richard Fitzhugh in front of a Beckman analog computer, and what he does is he implements a model of a neuron. He was a neuroscientist, and he was one of the main figures who developed the mathematical foundations for the actual understanding of how biological neurons work on an analog computer. Here you have another analog computer and more analog computers and analog computers and analog computers, and you see an interesting point. They grow larger. When you think about the problem we saw in the beginning, A times B plus C, on the digital computer it was 6 instructions. On the analog computers it was 2 black boxes, one implementing the addition, one implementing the multiplication. Oh shit, you need as many computing elements in your analog computer as your problem has. So if your problem needs one integration more than you have integrators on a particular machine, you can't solve it. That seems like a problem, because on a digital computer you don't actually care how many operations you need. You can always exchange complexity with time. You just wait longer. And you remember Landau O notation, have fun waiting when it's maybe 2 to the power of something nasty. But an analog computer can't do this. The analog computer, the machine itself, has to grow linearly with the problem. That was a problem in the 60s, that is 1960. As you see, you could fill a whole room with many analog computers who were all working together on a single problem. Nowadays, that's no longer a problem. When we have analog computers in integrated circuits where we have hundreds or thousands of computing elements on a tiny sliver of silicon, it's basically not a problem. Just plug in another accelerator card and you have 1,000 additional computing elements. Back then it was a problem. An analog computer, however, has an incredible advantage. Your digital computer program gets slower and slower the more complex your problem gets. The analog computer has a constant time to solution. It does not care if you solve one differential equation or 10 coupled differential equations. It uses the same amount of time. It just uses 10 times the computing elements. And that is really fascinating, because when we have constant time to solution basically on an analog computer, we can tackle problems that are out of reach for digital computers in principle. So let's have a quick look at how to program such a machine. I will just dive into an actual problem. You have, I'm sure, seen and heard about the Lorentz chaotic system. Lorentz was an atmospheric researcher, and he discovered the first chaotic system on a digital computer of all things. Unfortunately, an analog computer would be much more well suited. And he realized, oh, that is a system that is so incredibly sensitive to tiniest changes in its initial conditions or its parameters that you can't basically predict it for any reasonable amount of time. And this particular system is described by 3 differential equations that you see on the top. X dot equals sigma times y minus x, and so on. And that is the ideal problem class for an analog computer. Whatever you can describe as such coupled differential equations works like a charm. And on the bottom you see the actual analog computer program. And what you see here, for example, that is an integrator. And that integrator yields x minus x. Ignore this change of sign. And you see the x dot equals sigma times y minus x. When this is minus x and I feed it back into the integrator, I already have the x dot equals sigma times minus x term. Wow. I have an integration of one term with just one feedback line. And I also need a y term with some scaling factor that is also fed into the integrator. And if you are used to it, and it doesn't take long to learn how to program an analog computer, after 1 or 2 days you are up to speed, you can basically transform a set of equations really without much thinking about it into such a computer setup. And you could now implement this program on an analog computer like this, and you could let it run and observe its output. And its output will show how the system you implemented actually behaves. And here you see how it was implemented on the predecessor of this small analog computer. You see a bunch of wires. And now it gets interesting because no one wants, except me, no one wants to patch that many wires. I really love that. But it would be ideal if we got rid of the wires and had something called an auto patch. And you can imagine an auto patch basically as a big matrix of switches, like a telephone exchange in the early days before we had voice over IP. And here you have a basic structure of a reconfigurable analog computer. On the top left, you have computing elements, integrators, and multipliers, and some constants. And on the top right, you have a matrix of switches. The switches are not shown, but everything where you have a column and a row line cross, you can imagine a switch. And these column lines are then connected to multiplication units, C0, C1 for coefficients, and they go into another matrix from which you can distribute the signals to other computing elements. And the cool thing is you can couple this with a digital computer, and ideally you have a compiler, and you feed your problem into your compiler, and the compiler will figure out which of these switches have to be closed and which coefficients have to be set to which values, configure the analog computer, let the analog computer run, and just read out the result by using analog digital converters. And that works like a charm, I have to say. Here you see the actual implementation of this Lorentz system in an abstract, in the domain-specific language. And you see let diff, blah, 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 let diff, let diff. These are the three differential equations. And you see let diff x comma t. This already hints at the fact that we can also solve partial differential equations where your integrations do not only run with respect to time. And that is everything you have to write. And the rest is then compiler magic that reconfigures an analog computer, and that is your output, a purely analog output, a perfect Lorentz attractor computed in the analog domain without needing to execute any algorithm at all. So that is only a small example, and the most important point is no patch panel. That is just for educational purposes and for people who really like to shoot themselves in the foot by patching complex programs. We already have a domain-specific language, we have a compiler nowadays, and we also have the hardware which we can program with these tools. And let's have a look at what is out there in terms of project. The first highly integrated analog computer was implemented 2005 by Glenn Edward Russell Cohen as part of his PhD thesis. And this was an analog computer that was used to solve stochastic differential equations. And that for the first time showed that the notion of analog computing is really well suited to be implemented in modern CMOS technology. 11 years later, Ningguo implemented a better and more complex analog computer also in CMOS technology that was, like its predecessor, freely programmable but offered much more computing elements. Unfortunately, as so often with academic projects, nothing came from it. Both got offers from big IT giants, which they couldn't decline, and that was the end of the respective projects. Both are working for evil companies now. What we can also do is quantum-inspired analog computing. In the beginning, I said a quantum computer can be regarded as being an analog computer. And interestingly, we can also do some things that are typically attributed to quantum computers by using classic analog computing means. For example, we can solve NP-hard problems like this in constant time, for example, max-cut problem. So as long as you can transform some nasty problem into some form of a max-cut problem, you can solve it on an analog computer in basically constant time. And that is done by, you see here, the output of a machine with 4 analog qubits, so to say. I would prefer calling it A bits, because it's not really quantum bits. And you see, these are oscillators, and we encode information in the phase relationships of these oscillators. So if you have an oscillator which has a phase relationship of 0 degrees with respect to some reference oscillator, that would be a 0. And if it has a phase relationship of 180 degrees, it would be a binary 1. And then we can just let physics solve problems in that we allow these oscillators to synchronize with each other with different coupling weights. And that actually makes it possible to solve NP-hard problems. Here you see our lab prototype of an 8-bit analog machine that implements a so-called oscillator-based easing machine and is capable of solving max cut problems with graphs of up to 8 nodes. Then another application area, edge processing, wherever you have,
Someone asked, from what I understood, analog computers are customized to specific tasks, which is very similar to quantum computers, and also the areas where it is advantageous is similar to quantum computers. Thus, my question is there any advantage of analog computers over quantum computers?
Shall I repeat the whole question? Shit.
Maybe.
Yeah, okay, so the question was, do I have analog computers any reason to be there when we have quantum computers? Basically, I have yet to see a large-scale quantum computer that actually works reliably. There are still many open questions with respect to error correction, how to build actual logical qubits from sets of physical qubits, but try solving a differential equation on a quantum computer. That's not the right class of problems for a quantum computer. Quantum computers are, or at least maybe, well suited for optimization problems and combinatorial problems, but an analog computer is really ideally suited to solve anything that can be described by coupled differential equations and partial differential equations. So that's not they are not competing, they are complementing each other. I personally would love to have a quantum computer for combinatorial problems and an analog computer, both as co-processors to some supercomputer, some digital supercomputer, and using the analog co-processor to solve dynamical systems problems based on coupled differential equations. Whenever you have to leave the digital domain, so whenever you have to interface with the real world, you need some edge processing. And there's a company called Ophase. They manufacture pretty simple field programmable analog arrays, which you can use, for example, for audio processing. If you dislike the idea to sample your audio signal, transform it into the digital domain, then throw a bunch of transformations on your signal, and then transform it back to actually hear something, you can use one of these chips that were developed by a company called Anodyne that was bought by Ophase, and do your signal modification directly in the analog domain. You could filter it, high pass, low pass, band pass, you can add oscillators, whatever you want, directly in the analog domain. Then you have, of course, artificial intelligence. And in the most simple case, just solve your linear algebraic problems with an analog computer. And the most straightforward idea is pursued by a company called Misc AI. Why not do your matrix vector operations by using matrices of resistors? And that's exactly what they do. You have large matrices of resistors, and these are programmable resistors, and you input a vector that you will want to multiply with this matrix as currents, and then you have Kirchhoff's law, and you get the result out of your matrix instantly, without loops, without loop optimizations or something like that. You have basically O of 1 for your matrix vector multiplication. IBM as well has unveiled an analog LLM accelerator. I love the picture. They really know how to make cool pictures and advertise things. And the tiny chip in the middle you see, that is IBM's interpretation of an analog coprocessor for artificial intelligence. They also basically implement matrices of resistors, but they use a different technique to implement the reprogrammable resistors. Then there's something like Endcard. They do very similar things. They come from trigger word detection. And here's something where I had my hands in. As I already said, I'm not happy with the current state of AI because I despise the idea of boiling down everything to linear algebra. I just think it's too simple, and there's a reason why nature doesn't do it like this. And this, for example, is an actual pretty good, also simplified model for a biological neuron, a so-called Hindmarsh-Rose neuron. And you see these are three coupled differential equations, and these are ideal to be solved on an analog computer. And here you see on the left-hand side the actual program for a single neuron on an analog computer. On the right-hand side, you see the behavior of the neuron. And if you ask a neurophysiologist, they will say, wow, that looks really, really realistically like a biological neuron. And an interesting point is, why not actually use biologically correct neurons to implement artificial neural networks? There are people who are working with sometimes human neurons, brain organoid computing, for example. I also find it quite funny that you can think of computers which need sugar to live, to compute, however you will call this, but adopting nasty and messy biological processes, I'm not so happy about this. But we could use analog electronics to implement really realistically behaving artificial neurons. There was a paper at the beginning of 2026, at the end of 2025, published by a research group in Frankfurt, the Ernst Strüngmann Institute. They have another approach on artificial intelligence using coupled oscillators. And when you remember the easing machine I showed you, my oscillator machine to solve max cut problems, that's pretty similar. And of course, that is ideally suited to be implemented on an analog computer, which is something we collaborate with them. Then general purpose analog computing, you have seen that is how we started, we as a startup company. I collect analog computers since I'm pretty small, since I'm 14 years old. This topic never ceases to fascinate me. And many years, about 10, 12 years ago, I decided, okay, it's time to build another homebrew analog computer, just to have not a historic analog computer, of which I have many, but they tend to break down like a historic car would break down, and thus I set out to build my own analog computer. And then a friend visited and he said, oh, cool project, let me join in and I will make your PCBs for this analog computers. And that was the very first more or less professional machine that I built, and I posted a picture on Facebook, and I got an order from a university in France. We would like to buy one. And then my wife and I sat down and built a second one, all surface-mounted components, and we were populating PCBs on our desk in the living room. And then we got another order, and then I decided together with 3 friends, okay, let's fund a startup company with the goal of bringing all this onto a chip. So that is no longer to be sold. The next one you have seen is this analog thing. And here you have an actual example that is not staged. That is from one of our customers, Ulm University. They use it for reaction kinetics in biochemistry. And here you see a great example for when your problems get more involved, more complicated, you need more analog computing elements. And in this case, you need 4 analog things to have all the computing elements you need to solve the single problem. But you see also it's completely trivial to parallel analog computers because you have no bus systems, no memory systems, no semaphores, nothing. You just have a bunch of wires carrying some voltages between computing elements. Then we now have that is our first system that has no patch panel anymore. The cables on front are just used for testing purposes here, but they don't implement a program. That was our first machine that is fully reconfigurable. No patch panel, nothing, just an Ethernet jack on the back and this rather simple protocol which you can then use your digital computer with our compiler for to actually solve problems on this standalone coprocessor unit. That is our largest system, and that's the largest analog computer in the world. 1,000 integrators and 500 multipliers. Imagine you are able to solve 1,000 coupled differential equations basically in an instant on this machine. And it's still not using highly integrated CMOS technology. It's basically using off-the-shelf discrete analog components. And this machine was bought by the DLR, Deutsche Luft- und Raumfahrtzentrum, and they use it for an incredible wide range of applications. For example, the aerodynamicists in Göttingen are working on implementing aerodynamical simulations, so computational fluid dynamics on the system. Artificial intelligence people are using it for reservoir computing. The quantum computing people are using it to simulate quantum computers on a gate level. It's really interesting because I haven't foreseen any of these applications. These applications basically came out of the wild. When the machine was there, people came, oh, I have a cool idea, can I try it? Of course you can try it, and it looks very promising what is currently happening. And that is what we have currently in the lab. Being a hobby electronics buff my whole life, I remember vividly my first homebrew printed circuit board, and now we have our first, not homebrew, company brew silicon. That the chip in the middle was our first tape out, our first CMOS chip in 65 nanometer technology implementing analog computing elements, which are here put through their paces on this evaluation board. And we currently have the second generation in our lab, which already contains basically everything we have here on a square millimeter or something like that of CMOS real estate, but with a bandwidth that really outperforms the simple analog thing by several decades. And with machines like this, we can solve typical differential equations and systems of those in way under a microsecond. That is faster than a typical system reacts to an interrupt from an external source. In this time, our analog computer already has the solution of some nasty problem. So thank you all very much for your interest. And if you have questions, let me know.
One question was, why is information still transmitted by wires? Is it possible to use light for faster data exchange?
Light seems charming at first. When you have a look at how fast an electric signal propagates through a wire, you will realize that you are at about 2/3 of c, 2/3 of the speed of light. So there is not that much potential to be gained by using light. The problem is with light, you can implement things like linear operations, multiplication with a constant by extinction coefficient in some metamaterial. You can add things, so you can implement basically the foundations of linear algebraic operations. There are several companies building photonic chips for this, and in Heidelberg, in Heidelberg is a large research group working on this. But for things that interest me, solving differential equations, at least I have no idea how you could implement an integration operation with using light only. So I think the gain of propagation speed is very limited. You could get from 2/3 of c to nearly c, depending on the material and its Brechungsindex, whatever this might be in English. But it is much more complicated than implementing basically classic CMOS technology with proven fabrication technologies. So highly interesting, but not my cup of tea personally.
It seems like analog computing is much further in progress than quantum computing. Why is it then that analog computing is much less popular?
I think the main problem is the name, analog computing. I realized whenever I talked with some venture capital company or the like, what, analog? That sounds outdated, that sounds boring. That is the main problem. So I should also start talking about natural computing or physical computing. And yes, it's further developed than quantum computing, mainly because it's much simpler than quantum computing. Try to implement a usable logical qubit. That's horribly complicated. Implement an integrator or a summer in CMOS technology. That is not simple, definitely not, but it's by far not that complicated like trying to get a quantum computer with thousands or millions of logical qubits working. So the technology is simpler, but the wording is just, yeah, unfortunate.
That's it.
Oh, that's it, okay. You were first. How do the neural analog modules scale with respect to jumper wires. I don't hope yet you have to wire them manually. Basically, when you have a look at actual biological brains, you will newer, nicht neural, okay, newer ones. When you get one advantage of the classic patch cables is you are not limited with respect of what you can implement. If you can think it, you can patch it. When you have matrices of switches, somewhere you have to start compromises. You are not able to implement an all-to-all connectivity when you have enough computing elements. In this machine with its 1,000 integrators and 500 multipliers, all-to-all is basically impossible. So what we did is we analyzed a lot of typical problems and used this as the basis to derive a hierarchical interconnection structure for this machine. But basically, as a rule of thumb, the density of your interconnect gets lighter and lighter the further you go away from a particular computing element. So we have clusters of computing elements, a so-called M-Redac, a module of a Redac system. They are very well connected, but from one module to the next module you have fewer connections, and from one chassis to the next chassis you have fewer connections, and so on. So it's not trivial for the compiler to actually figure out how to couple the computing elements, because the placement of the computing elements has a big influence on how the interconnection density is between your computing elements. Does that answer your question? Okay, then you. Okay, so the question is about scaling. How have they scaled in the past? How are they scaling? Is there any means in building larger and larger computers? In the past, the examples you have seen, classic analog computers basically topped out at a few hundred, maybe 1,000 computing elements. That was basically the end of what was practically possible without filling more than one room. When you have analog computing elements in CMOS technology on a chip, you can basically have hundreds or thousands of computing elements on a single chip, and you can have multiple chips on one printed circuit board and several of these in the chassis and so on. Basically, there is no such thing like enough computational power, neither in the digital domain nor in the analog domain. In the digital domain, we increase clock frequency, we increased clock frequencies, and we increase the number of nodes. In the analog domain, we need more and more and more computing elements. When you, for example, think about computational fluid dynamics, where you solve partial differential equations, one pretty simple approach to solving partial differential equations on the analog computer is to discretize your space along the x, y, and z axis. And basically, you need a three-dimensional structure of computing elements. So even if you have 10 positions along each axis, you need 1,000 computing elements. So yes, we need thousands and prospectively millions of computing elements to solve realistically large problems. Yes. Basically, we have this down to maybe a square millimeter. And that is just a test chip that can be further improved. So having hundreds or thousands of elements on a single integrated circuit is no problem nowadays.
One last question. Will analog computers quicken the breaking of classical non-quantum safe encryption? And if yes, do you think that's an important problem, or do you think the race against quantum computers is the greater risk?
That is a difficult question. About 4 or 5 years ago, I would have said there are quantum computers here and analog computers there, and they have nothing to do with each other. Then there was a Nature paper showing that you can solve max cut problems using an analog computer, and I personally was flabbergasted by this paper. I never thought that an analog computer could be able to solve a combinatorial problem. Honestly, I have no real idea how I would do encryption, decryption, cryptanalysis on an analog computer, but this does not say there is no way. It's just I don't know of any way. Interestingly, when we had this 8 oscillator easing machine, built from our analog computer elements. One of my colleagues came up with a scheme of basically implementing a factorization algorithm is the wrong word, a factorization program on this oscillator-based machine. Also something I did not think about previously. So yes, I think potentially analog computers might, for example, be able to factor large numbers, but I have no idea if this is really a viable approach or not. So I just don't know, honestly not. We try to make it a huge venture. We have to pay the salaries of our employees, which are quite a lot by now. But it's much more difficult to explain to people what we are doing. It should be more difficult to explain to people what you are doing when you are doing quantum computing, because nobody understands this, but people always think, oh, quantum, that sounds cool, that sounds hip. We will invest, but when you build analog computers, it's really hard to convince people invest, because that is a really important future technology. So it's not a hobby horse. Definitely not. There. We started with 4 people about 5 years ago, and we are now at, I think, 26.
I think the Ophase-Leitung will now want to quit this slot because of time, and yes, so.
That is a funny thing, because what I do as a professor at the FOM has nothing to do with this, fortunately. But if you are interested, for example, in classic and modern analog computers, feel cordially invited to either visit me at home, that is near Bad Schwalbach, just send me a mail. And it's the world's largest collection of classic analog computers. Most of them are in working condition. Or hop by in Frankfurt at our labs, let me know in advance, and I can show you what we are actually doing with chips in the lab and our IC development people. Feel invited, just let me know, send me a mail. Thank you very much.
We thought the usual Miscs are not good enough, so it's hard to find an analog computer in Lego, but we thought we found like a Macintosh. Maybe ja, vielleicht haben Sie Spaß.
Definitiv. Vielen
Dankeschön. Ne? Vielen Dank, dass Sie gekommen sind.
Wir können uns gerne duzen.
Vielen Dank, dass du gekommen bist.
Sehr, sehr gerne.
Hoffentlich kommst du nächstes Mal wieder.
Auch sehr gerne.
Wunderbar.
Gut, dann macht's gut.
Danke. Kommen Sie gut nach Hause.
Danke, dass das mit dem Vorverlegen geklappt hat heute.
I'm from the AStA. Hi. Yes, okay. My name is David. I'm from the AStA. And today I will be presenting the AStA to you. This is the first time I'm doing this presentation in English, so if anything you don't understand, feel free to ask me questions when you don't understand something or at the end, whenever you want. First, welcome at TU Darmstadt. So, who we are. This is a photo of some people in the AStA. It's a bit old. But yeah, the AStA is the central representative body of the students at TU Darmstadt. So you are all able to vote for the student parliament, and the student parliament then elects the AStA. So the AStA is like a government of the student parliament. And yeah, we offer services, events, and support, and we are also politically active. We have 5 elected and 24 appointed representatives, and a number of permanent employees and collaborators. I am one of the appointed representatives. The representatives have all their own topics which they are responsible for. For example, I'm appointed for the queer office, so I do events for queer students, and students can contact me if they have questions, if they face discrimination. But we also have many other topics for housing, health, political, education. Is everything okay? Okay. Sorry. Yeah, here you can see some photos of events and demonstrations that we did. We advocate for fair, inclusive, and supportive university for all. So, yeah, for example, this photo you can see at the top, the government of Hessen recently wanted to, or they have cut funding for the universities, which led to the closing of some departments, and we protested that, and it might also lead to higher sums that have to be paid by the students each semester. And yeah, we also oppose all forms of discriminatory policies. And yeah, here you can see some pictures. We also organize all kinds of events. From cultural and networking spaces to discussions and lectures, workshops, the autonomous tutorials, which I can still tell you a bit more later, and many more. We also have many cooperations with other institutions in Darmstadt outside of the university, with these 2 theaters, for example, and the museum, which is, I think, in this direction. It's very close to the university if you walk here. And these cooperations mean that you can use these cultural services for free, which the AStA organized. So you can go to the Staatstheater. If 3 days before an event there are still tickets left, you can get them for free. You can also get free tickets at the Theater Mollerhaus, and you can enter the Landesmuseum for free if you show your student ID. On the AStA website you can find more information about how to get these free services. And there are more cooperations. Also regarding mobility, first you've probably heard of the Deutschland-Ticket, which means you can use the local public transport all over Germany for free. You've probably installed this already. This is also organized by the AStA. But if you want to rent a car or bike, there are also cheaper deals with some services. You can again find more information on this, about this on the website of the AStA. And if you have problems during your time studying here, there's many things where you can reach out to us and we might be able to help you. We have a lawyer where you can book appointments if you have legal trouble, and you can get legal advice from our lawyer regarding legal advice. We also have help for internationals, where you will get more information about in a minute. And we also help regarding labor law for student assistants at the university. There you can also, about this topic, you can also get legal advice. And if you if you experience other types of issues at this university, always feel free to reach out to us. Maybe we will be able to help you ourselves, and if we don't, we probably know who can help you and point you to them. So if you experience discrimination, if you have a job at this university and you're expected to do overtime, but you're not paid for it, any of those issues, feel free to reach out to us, and we'll see what we will be able to do or who we can point you to for help. Then we also have other corporations or parts of the AStA where we employ people, and it's for example, this cafe, it's 806 QM, or it's also sometimes called 221 QM. It's if you go in this direction, then it's very close. It's a cafe where you can study and meet up with friends, and it's a bit cheaper than the commercially done cafes. And similarly, we also have the Schlosskeller. You might have seen the Schloss on the opposite side of here, where it's also a university building, where there's also a small museum in it there, but most of the Schloss is also university. Some lectures are done in there, and there's some administrative stuff in there, but there are also two AStA things there. First, the Schlosskeller, where there's parties, concerts, shows, films, a lot of events. And opening next week again, the Schlossgarten. It's a bit like a beer garden. And in the summer, you can get drinks there, sit in the sun. It's very nice, I would recommend. This might be less relevant to you because it's at the Lichtwiese, so it's at the other campus. It's a store for stationery and paper stuff. But I think it's also more important to other subjects than to you. Then again, right around the corner here, we have the 20 degrees, 20 Grad. It's a bicycle repair spot. So you can't just go there and give them your bicycle and they will fix it, but they have all the tools. So if you have a bicycle and it's broken, you can go there, and there are also people there who are able to help you fix it, and they have all the tools that you might need for fixing your bike. And I think I'm almost finished. Yes, now some upcoming events. The autonomous tutorials I already mentioned at the beginning. Those are tutorials, so kind of small classes, but they are held by students who can who choose the topics. And I think most of them are in German, but there might also be some in English. You would have to look it up. And it's not, you can't get credit points or anything through it, but it's a nice opportunity to learn about topics which don't have as much place in the regular academic schedule, and do this with other students and in a less hierarchical atmosphere. Then we have a talk coming up about fraternities and a criticism of them through a feminist perspective. This talk is also in German, so it might not be interesting to you if you don't speak German. And then organized by me and the queer office at the other university here in Darmstadt, we have a picnic coming up in the Herrengarten, right in this direction, for queer students, friends and allies. This will be done bilingually, So we will be speaking German and English, and I'd be very happy to see some of you there. So feel very invited to come around. And lastly, our contact. We also have an office in this building, in this direction. That is the opening times you can find on the website. There you can come if you have any issues. Also, all of this information which I've just given to you, you can find at our website, which is not on here. Sorry. But if you Google Asta TU Darmstadt, you will find our website. And I would recommend you follow our Instagram or Telegram channel where you can get all the information about our events. I hope this was somewhat understandable. Do you have any questions? Okay. Then you will learn more next about the program of the ASTA to help international students.
Thank you, David, for your presentation about the ASTA. If you guys have any more questions about after the presentation or in time, like he said, you can go to the ASTA. Yeah, so now we have Harsh from Tutor International. Okay, then the stage is yours.
Hello. So, welcome everyone. Good morning. I hope you guys are not sleepy or too sleepy. Let's go ahead with the next presentation, of course, which is Tutor International. We are here for the students, and if I really summarize it up very fast, it means we are a student organization, and we organize events for you guys. It's for all the students, exchange semester, normal students, whoever would like to join us. And that's how it goes. We have divided the events in two terms. We have monthly events and weekly events. So in monthly events, we have one event each Saturday. And in weekly events, I'll be talking on later ones. Let's go ahead with the first Saturday of the month, which is every month. The first Saturday is going to be the creative evening. What we do there is we organize any kind of creative activity like drawing, sketching, painting, henna, for example, art and crafts. We use trash to make good stuff out of it. It's very interesting. Then going ahead with the second event of the second Saturday, we have cultural evening. There we travel to different countries, different cities. We explore the culture. We have a presentation of how the status is, what's going on there and everything. With that, we also have food there. From those specific countries, we have music from those countries. We have dance from those countries, depending on what the people would like to have. Going ahead with the third one, we have activity, which means we explore Darmstadt in terms of what we can do here, because it's a small town. Many people get bored here. So you should know what are the things to explore. We go to different, for example, this was Kegeln. We go bowling, we go pool playing, we have board game nights and different activities. Further on, we have a very cool thing which is called excursions. Not only Darmstadt, we explored Hessen. Wherever we can go in the time period of 1 to 2 hours, hopefully, we go and explore every place near Darmstadt. We have been to Heidelberg, everywhere, Frankfurt, small towns, different castles. So you guys can join us if you are new in Germany or you have not explored Hessen too much. Just look it up. We go there, we have a full itinerary of the day where we can travel and everything. We come back in the evening again. And that's all with the most important monthly events which we have. And after that, for the people who like books, writing, reading, we have once a month book club. We go there, we talk about books. We write if you want, we read if you want. It's different topics each time. You can see it up, how we have planned it. Now coming on to the next things, which is this semester, actually the last semester we have incorporated a special event, which is the Girls Walk. It happens every third Sunday. You guys can join it, whoever would like to go around. They go walk in Rosenhöhe, they walk in Herrengarten, they plan their walks, they go around in cafes, and have a really nice time. We have quite a lot of events, and with that, we also have weekly events, which is every Friday we have something called Meet and Chill. We go to different cafes. We go to, for example, the one from Asta, he mentioned that we have Cafe 221. We go there very often. They're quite annoyed from us. But other than that, yeah, we do cafe hopping. We go everywhere. We take board games with us. We play there. We chill and meet. You can meet new people there. You can find new friends there and new community. Then we have something called study time out. When you are in the stress of exams and you think you've not studied anything, then you guys can join us. You'll find people who are studying the same thing as you. You might find study buddies there. We also have healthy snacks there all the time. That's me. I was not studying. I was most probably sleeping. But yeah. Going ahead, we have something called accompanying service, which means if you're really confused about what to do and you don't know what to do and you don't know how to go to Asta, or you have to go somewhere where they speak German and you don't know German or anything, any sense, you can always contact us with email, and we will have a tutor who's going to accompany you with you for whatever help you need. They're going to be there the whole time with you guys and help you out with whatever situation you have, regardless. So with that, if you go on our Instagram channel, you'll see we have upcoming events, which is today is 9, tomorrow is 10. We have Meet and Chill tomorrow in the evening. Then we have TE Starter Pack. They're going to explain everything you need in Darmstadt as a student on the 18th of April. And then we have Karaoke, which is one of the most famous events which we have. It's in Schlosskeller. It's nearby. We basically do karaoke and we sing and dance, and it's quite fun. So going ahead, Tutor International, this is all of our information. This is our Instagram, our Facebook, our Telegram, and our website. Most of the time I prefer Instagram because it's very easy and convenient. You guys can scan this QR code, by the way, and you'll find all the links, and you can join it. You can see it. All of our updates are on Instagram and all the other platforms as well, whatever you're comfortable with. Please follow us there, and hope to see you in the next event. Well, that was quick, and that's all from my side. Thank you very much. I hope you enjoyed.
Thank you so much, Harsh. So now we will have a small video presentation from Wolf Hertlein. He's going to explain us about the general complaint management here at TU Darmstadt, and maybe some words at the end about studying here as well.
I think we impose critical stress on our streaming team with the video presentation. I'm very sorry for that. So let's check if that works or not. Just 1 second.
Hello and welcome to TU Darmstadt. I would like to talk to you in short about complaint management and the Officer for Students with Disabilities or Chronic Diseases at TU Darmstadt. Who am I? My name is Wolf Hertlein. I'm for a long time now at TU Darmstadt and in the role of the complaint manager. From my origin, I'm a mathematician. I studied at 3 different universities in Germany, and I do complaint management at TU Darmstadt now for a long time and have a lot of experience. What do? I accept and deal with complaints and other types of feedback from students and all other people at TU Darmstadt regarding studying and teaching at TU Darmstadt, including teaching, of course, studying, infrastructure, administrative services. I accept complaints against persons and the organization of studies. What do you get from it? I work completely confidential, of course, and very informal, so I can address anyone who is in charge or I hope to get information from. I am neutral. I'm mediating between the different parties. So you on one hand, on the one side, and staff of the university typically on the other side. What do you get from it? In the best case, you get a solution for your problem. In the worst case, you just invested your time and have no problem. Especially in exams, which is in German called Nachteilsausgleich, in British English reasonable adjustment, in American English academic accommodation. Whatever term you like, I'm supporting you and help you, and in this case not neutral but very supportive. So please address me if you have questions regarding reasonable adjustments or academic accommodation, and I will give you advice and try to help. I do not decide anything. These things are decided at your department by your Studienbüro, where you can also applicate for your accommodation. But I support you to get what you need. Studying at TU Darmstadt is a good choice, but it is also very, very challenging. If you have experience with German universities and studying computer science at German universities or other scientific studies, you will please exchange with other students from other universities, from international universities, so they can also get some experience, some insight of the type of challenging you have at a German university. It is at all possible to study, and I hope you have a lot of fun with it. What I would advise you to stay tuned, to study successfully, build a learning group, which is very important for students in fields of study related with mathematics and structure. Know the rules, especially the rules how to find how to deal with Tukan and Moodle, for example, and ask for help if needed. So I hope all the best for you during your first semester at TU Darmstadt, and if you need me, please address me. Thank you very much. I'm Wolf Hartlein, the Complaint and Improvement Manager at TU Darmstadt and the Officer for Students with Disabilities or Chronic Diseases. Thank you.
Great. On a personal note, Wolf is a great choice to go to as a first step if you have any issues. If we can't help you, or if you don't want to go to us, go to Wolf. He's nice and he won't tell anyone unless, unless you tell him to. For now, if I'm not mistaken, that's our last talk for this program point. The Gender Equality and Unite team are not here today, and that means we have a slightly longer break than anticipated, up until 1 p.m. So for around an hour and 20 minutes. That's enough time for you to, in theory, go to the Mensa and get some lunch. But at 16:30, I think, no, at 2:30, we will have the Master Barbecue, where you also get food if you want to. So you can decide whether to go to the Mensa or not. Thank you very much, and see you later at 1.
Okay, so hi everyone. Thank you for sticking around, even though it's not too many people anymore. I have brought with me 3 students and 1 PhD student, and our plan is just to answer some of your questions and maybe give you an overview and some helpful advice from students who've been here 1 or maybe many years on what lectures would be good to choose, or other strategies for your studies. Feel free to ask questions throughout the whole panel. Just raise your hand and shout them at us. The idea is just to make this as helpful as possible for you guys. The first half will be on stream as well, and then after we've all answered all of these questions, we'll cut the cameras to discuss a few more delicate topics. So maybe save those questions for when we cut the stream. Sorry guys for your at home. We can't stream that part. And maybe to start off, we'll just do a quick introduction round. The idea is just to say your name, which master you're studying in, or which research area for our PhD student, then which semester you're in, and maybe as a fun side fact, your favorite place in Darmstadt. So to give you some preparation, I'll start off. I'm Sebastian. I'm studying the German Computer Science Master. I'm in my 6th semester. And I'm currently writing my master's thesis. I hope to submit it end of April, so not that long to go anymore. And currently I'd say my favorite place in Darmstadt is Herrengarten. You've probably already seen it. Especially during the spring, it's really nice there. Should we just do from left to right?
So, welcome. Many of you have already seen me yesterday. My name is Jannis. I'm a PhD student here in Darmstadt. I am researching reinforcement learning in the group of Christian Kersting. But before that, I also studied here and did my computer science master and as well as my internet and web-based systems master, both here at the TU in this department. And I think my favorite space is the Rosenhöhe, which is a park area northeast of here. You can walk to that. It's, I think, 15 minutes, 20 minutes. And you can chill out there, and it's really great in summer. So there is a lot of green in Darmstadt, and it's a good start to see what Darmstadt can offer.
Hi, my name is Annike. I'm in my 3rd semester now of the German Computer Science Master, but I'm also doing like a lot of the stuff that overlaps with the AI Master, so I can maybe answer some questions about that, but I'm not studying the AI Master. And my favorite place in Darmstadt is probably also Herrengarten, because I can watch some ducks there, and I like the ducks, especially in spring when they have like cute little babies.
Okay, hi. My name is Patty, and I'm starting my 3rd semester in the Master IT Security here at TU Darmstadt. And I can answer, hopefully I can answer all of your questions regarding this master. And my favorite place in Darmstadt would be the Herrengarten, but it was also mentioned before. So I would suggest like checking out the Kaffee Chaos.
Hi, my name is Toby. I'm studying autonomous systems and robotics. I'm in the 6th semester and writing my thesis. And my favorite place is next to the Herrengarten, the Prince Everywhere Garden. Yes.
Okay, now that we've got the introduction round behind us, maybe you will just do a bit of general tips on how to structure your studies, since that's probably your first big tasks over the next few days and weeks. Just say if you want to answer it. How do you go about choosing your studies or your courses at the beginning of the semester?
Okay, so I always start by choosing many courses, well over 30 ECTS, and then cutting them out throughout the first weeks of the semester. So I will be visiting a lot of courses and then cutting those who are not fitting what I expect of the courses. So this is like my preferred way to go about all of this. And also, please don't miss the seminar and lab kickoffs in the first 1 or 2 weeks of the semester, because later on you will not be able to join them anymore.
Also about the practical labs and the seminars, since we have a lot of students nowadays and we don't offer enough practical labs for everyone, it is important that you choose maybe 2 or 3 practical labs or seminars, go to the kickoffs and apply for them if they have an application. If they are open for everyone, that's fine, but most of them will have some form of, we only accept 30 students and you are 60, so we have to cut out the half. So it's not guaranteed that you will get every practical lab you want. As such, it's important that you don't stress yourself with one practical lab, go for 2 or 3, check out, and if you've got more than one spot, it's easy to say, sorry, I do another, or I will not do this practical lab. So then they can give this space to another group or another student. But it is common that you will maybe not get the practical lab you want, especially if you go for the reinforcement learning or the AI labs, where we say, for example, we have 30 to 40 room for 30 to 40 students, and we have over 100 students want to take them, which can bring us to a little bit of a capacity problem. So that's just as an information for you.
Yeah, so you've probably noticed that the whole choosing courses, it's quite spontaneous and flexible, and you usually look on a per semester basis, what fits in your study plan, and then what you want to take. So, I mean, not every course is offered every semester, but yeah, maybe to give you some more specific. Do you want to add?
Yeah, I have one more point. I'm not sure if Tim told that maybe yesterday already. In Darmstadt, we don't differentiate between bachelor program or bachelor courses and master courses. So every lecture you want to take can be done in the master or in the bachelor. So if you sit there and you have a lot of bachelor students around you, that's completely fine here in Darmstadt, because we thinking that we want to give a lot of opportunities. So if there is a specific lecture which may be interesting for you and it's more for bachelors, don't worry, you can also take this as a master student. So there is a shared, how is it called, lecture pool, you could say. Yeah. So maybe you have heard already from Tim that this is the case.
Yeah, then maybe to get a bit more specific, I just want to do a quick round and ask everyone, what's your favorite lecture and maybe your favorite lab or seminar? Want to start from the right?
My favorite lecture is Bildverarbeitung, as a German lesson. Yeah, I like it. I like the prof, and he's very fair.
Okay, so I cannot give you any recommendations on seminars or practicals or labs yet, because I did not take any so far. But I really liked the lecture on critical communications, CRACOM, in the winter semester, because it was more hands-on and you had labs, and it was really cool.
I can also recommend the network security lecture. I'm not sure which semester. It's offered in the summer, so you could take it this semester if you like. I mean, the course title probably says it, but there's some nice exercises which you can also do in addition to the lecture. You get quite a nice bonus for these exercises for the exam. Maybe we should explain that too. I'm not sure if you've heard about the bonus system, but there's quite a few lectures which have a bonus attached to them. So if you complete the exercises and submit them, you get points for those exercises, and you'll get a bonus of, say, 0.3 or 0.7 for the exam. So that will be added to your exam grade, and that's then the final grade you get. So that's an opportunity to maybe complete some stuff in the semester, which can give you a better grade in the final exam. The important caveat is that only helps you if you pass the exam. So if you don't pass the exam, then you also don't get the bonus, because there's a few lectures which offer a 1.0 bonus, so you get a whole grade better, and those would help you if you didn't pass the exam, and that doesn't work. But yeah, that's quite a helpful thing to do if you like to get a bit of a better grade by doing some extra work during the lectures. Yeah, and network security, they're quite nice as well. You can do like a CTF as part of those this bonus project, so pretty hands-on. And well, if that's something you like, I can really recommend the lecture.
I personally really liked scalable database management systems last semester. They have so 40% of the grade there is basically a practical lab kind of thing. So the algorithms, so it's about databases, database management systems, and the algorithms that you learn in the lecture, you then program in Rust in the lab then, and 40% of the grade is that lab, and then 60% is like a written exam, and I personally really liked it. Also the professor did a great job doing the lecture, and the PhD students who were responsible for the lecture were also really nice and always answered all of your questions. But yeah, you can't deregister after submitting the first lab. So if you want out of that lecture, it's not as easy as with other lectures, because other lectures you can basically deregister 7 days before the exam, and that's not possible in SDMS because the first exam is basically the submission of the first lab then.
So I would recommend, or my favorite lecture was Information Visualization and Visual Analytics, which is a cooperation with the Fraunhofer IGD. And you basically learn all around how to visualize information, what are good visualizations, what are bad visualizations. And I think that is very helpful for everyone, independent if you're doing IT security, artificial intelligence, or robotics, because at the end you have to write a thesis and you have to communicate what you want to show and what your results are, and this lecture is very general and very helpful for everyone. However, take it with a caveat, because all these lectures I took around 6 to 7 years ago with professors no longer at this university, so no sure if the lecture is still as good as it was 7 years ago. But it is still there. It is, I think, still offered.
I can add to this specifically because I heard from several other students that the lecture, this specific lecture, they took it the last semester and it was great. So.
Yeah, but I think you cannot choose it if you're studying autonomous systems and robotics.
Maybe then to add to this, maybe show of hands, who of you is studying the computer science or IT security masters? Because for those, okay, so it's a few people. For those, you also have to choose some Studium Generale modules, so lectures from other areas, basically. And for those, well, there's a lot of choice there, and maybe just we do another quick round, and we can tell what we did during Studium Generale.
I don't choose it now. I try it in Maschinenbau. There is a tutorial. It's full-time, 2 weeks, about robotics, and I want take this, but I was a little bit too late, and now I have I took some, or I have not chosen yet.
Okay, so the most classic solution for Studium Generale in IT security, because we only need to complete 6 ECTS, is just doing a language course. Most of the language courses are exactly 3 or 6 CP, meaning that a lot of the students just complete a language course. For me, I did a Finnish course. I will do a French course this semester, and last semester I just for fun I took a history course. It was pretty fun. So I did a bit more Studium Generale than would be necessary, but yeah.
Yeah, a big recommendation on the language courses. It should be noted though, they're quite popular, so there's a bit of a chance you don't get in the course you like, especially for languages that are currently quite high in demand for learning. They do have a they do have some measures to get you in a language course if you're doing a semester abroad, so then you're usually fine. But yeah, that should be noted.
Another thing about the language courses, it's mandatory to go there specifically, so you cannot skip a language course like more than 2 times in a semester or something like that. Otherwise, you will fail. So you need to be there for the language courses.
Let's stop talking about language courses. My recommendation is Eisenbahnsicherungswesen 1. I know they have changed the name in the last semester, so I have to check what the new name is. Bahnbetriebssichere Durchführung. It's about trains. If you like trains, as I do, Darmstadt has the Eisenbahnbetriebsfeld, the EBD, which is basically a miniature train station by the Deutsche Bahn, what is used to train their own people there, and the university has a cooperation with them. So you go there and basically you get credit points for playing with miniature trains, but with the real techniques and stuff they have in the Deutsche Bahn. So you basically have to go there and do a mechanical switch station. How is it called? Interlocking station, yeah. And you learn basically what over all the systems what we have in Germany, from mechanical to electrical to electric-mechanical to relay stations, and what a relay station is, and you basically get credit points for trying them out and play with them. And there are 2 courses. One is the normal case, where everything is fine, and then you have something like, oh, there is an earthquake, or something is done with your train. What should I do now? And it's quite fun, and it's, in my opinion, quite easy to get these credit points, and it's trains. So, nothing more to say.
So since I do the German computer science degree, we have like 18 CP of Studium Generale at least. So 18 minimum and 24 I think it's maximum. So in my first semester I did signal processing at the electrical engineering department. I really liked it, but I was the only one in there that was not an electrical engineer for a good reason, because usually you need deterministische Signale und Systeme, so you need another lecturer to visit signal processing. It's not an introductory course, but yeah, if you know something about Fourier transformation and C transformation, or you're willing to catch up on that and yeah, spend like 2 weekends watching videos and stuff like that, then I guess you could do it. Yeah, that's the problem. For most of the lectures you need like their base lectures, which they do in, and the base lectures, at least the electrical engineers don't recommend them because they're really difficult, and it's just Kampfrechnen they call it. So it's just calculating until your hand hurts really bad. Yeah. Last semester I did Technik Didaktik. I can specifically not recommend that. Don't do that. It was not a good lecture, and yeah, now this semester I'm doing a language course as well. Hopefully I'm going to get in, so I'm not telling you which one, so you don't go into that one. I want to get my spot. It's a European language, yeah. It's a Slavic language, so I don't think people are going to.
They don't try Chinese, you will not get in. Trust me.
For Studium Generale, I mean, we already talked about the train lecture. I can recommend that too. If you're the type that says, well, I'm not super interested in doing stuff from other areas, which, well, it's a nice opportunity, but what you can do to get around this is take a course from the Kommunikationsnetze research group, because they're part of the electrical engineering department. So technically, those count as Studium Generale. It's courses like routing, switching, forwarding, transport protocols, application protocols, resilient communication networks. So this kind of stuff, it's basically computer science, but you can take it under Studium Generale if you like. And then if you do want to do something completely different, I took antique religion, I think 2 semesters ago. Was quite a nice course, so we can probably recommend the history courses. You basically just sit in the lecture, you have to remember everything, and then the exams are they're really manageable. I mean, it's mostly multiple choice or very short answers, so yeah, I can quite recommend them for Studium Generale.
Specifically, the history lesson I did was Introduction to the Middle Ages, so great course.
If you have any questions, feel free to raise your hand.
Yeah.
I joined from some other university, and I just want to know where I get to know if I need to do some more courses for the IT Sec Master, and if you don't know what person I can ask.
Okay, in that case, always ask Tim Neubacher. So maybe write an email, after a week write another email, and in the best case just come by while he has his like open consultation office hours, and then ask him. It's about the Anrechnung from courses of other universities. And specifically, can you please repeat again what was the question about the IT security specific part about that?
Basically, you have some you will get this.
Yeah, so I think, yeah, it's about Auflagen. And you should, so, you know, you get like a letter of acceptance. You should all have gotten a letter of acceptance since you're here. And in this letter of acceptance, it says if you need to complete any Auflagen, so any classes. And if there's no Auflagen in there, you don't need to complete any of them. So it's in this letter. And if you have lost it, I guess go to Tim, but hopefully you still have that letter.
Yeah, nothing to add to that. Any questions in the room? Anything that popped up, or should I continue with my... Okay. I'll continue with the regular questions then. Yeah, maybe going a bit further to... this is probably relevant for you in 1 or 2 years, but looking for a thesis topic, how would you go about that?
Okay, so we do have some groups from professors and PhD students, and we have some like bigger, more involving more professor groups, like the Emergent City like it's not a department, but it's like group. We have the one about cryptography. It's cryptoplexity. Yes, right. And crypto, right, and crossing. Those are like bigger groups, and they all have their own websites, and they do publish any thesis topics, as well as in the floors downstairs, and also here in the Piloti in the first level. They do have those those blackboards, right? Thank you so much. And they do publish their thesis topics on these blackboards. So it is beneficial for you to just walk down the corridors here, look at the blackboards, and look at the thesis topics offered there. In any other case, you can always ask most of the times the PhD students whether they do have any other topics, and in my experience, a lot of the people are going about their thesis topics by choosing a seminar, choosing a lab or something like that, and then after the lab, after the seminar, asking the person responsible for the lab or seminar whether they could like continue their topic for a thesis.
You can also look at d120.de. There is a site with all institutes, and you can there's the link to them. And there's also an email subscription where you can get an email with new subjects, but there is not so many. I got 1 or 3 mails, and the most was from Jan Peters, and the information is also on the website of EIS.
The mailing list he was referring to is Abschlussarbeiten at d120.de.
In case you want to do a topic in a field like AI, where we got a lot of questions about that actually in the last years, it's often easier if you have a topic in mind. Write to the PhDs, say, hey, I have this interesting idea for a topic, for a thesis, and you will get more answers to these emails than just saying, hey, I need a thesis, can you give me a thesis topic? Because that is not as easy for us. We cannot offer a supervision for everyone, of course. I personally get 2 to 3 emails each week about thesis supervisions, and I can only accept maybe 2 or 3 each semester. That doesn't fit, of course. So what I'm looking at when I'm selecting students is if they have done practical labs with us, if they have some experience in the field we're searching for. For example, if you want to do a thesis with me, it is recommended for you to have some knowledge in Python, because we will program in the thesis, and most of our programming is done in Python in my group. Check out the websites of the groups you are searching for, like Jan Peters group, like our group, the IML group, and you will find some information about thesis. Maybe you will find topics which are open, but in most cases I would say it's easier for you to check the PhDs, check what the PhDs are doing, and then if that's fitting your idea for a topic, write them an email.
I can also add to that, it's really helpful to complete lectures, seminars and labs in the research group you're interested in before. So that is always helpful to get maybe a thesis topic. You work on some topic on in a seminar, then you have a short paper on it, and maybe you can discuss with the supervisor of that seminar, is it possible to make a thesis out of this, or expand on the topic in some way. So yeah, just going to lectures that you're interested in and talking to the people, that really helps you in getting a thesis, because there's so many people looking for thesis topics, and if the supervisor or the potential supervisor already knows you have some basic knowledge on that topic, it really helps. Yep. Okay, so the first question was that some courses have requirements and whether they're mandatory or whether you can still do them during the course.
So the requirements are not mandatory. There's nobody checking, have you already done this and this? It's just a recommendation basically. So maybe just go like to the first 1 or 2 lectures, and if you realize, oh, I don't understand like anything, or you know, they require like really deep prerequisites and knowledge. For example, if you, I don't know, go to the multimodal AI lecture and you have never heard about AI and neural networks before, it's still possible. You can try to read up on it, but it's just more work, you know, so you can decide on yourself. You're a free person.
the most lectures repeat the important things, and then you can get it.
There are the recommendations for a reason. If they recommend you to have some knowledge in statistics, you should have these to follow the lecture, or it will not be fun, so to say, or a lot of extra work, as said before. So check out and be honest with yourselves if you trust yourself enough to do the lecture. If the lecture says you need, or you should have heard, I don't know, introduction into AI, then maybe think about it if you think you have the knowledge, or are you willing to learn them by yourself? Because in the end, these recommendations are not because we think they are fun, but because you need them to follow the lecture.
But also maybe in personal experience, some lectures really list like 3 to 4 prerequisites, and sometimes that's like, for example, some machine learning lectures, they list like 3 or 4 prerequisites, and basically all they mean is, okay, you should have maybe had some introductory course to machine learning, you should have heard a bit about the basics, so you don't need to complete exactly those courses. As I said, maybe go into the first or second lecture, and then you usually notice, is the prerequisite way too much?
Okay, the next question. Yeah. So the question was whether you can do a thesis also based on your own idea. So yes, that's possible. You'll have to find a professor who supports that decision. So if you find a research group who does something similar, and then maybe ask them to supervise it, that could work. Another thing that is quite common at other universities is doing a thesis in cooperation with a company. That's a bit harder to work out here, so it's not impossible, but as always, the professors and research groups have their own interests, and if the topic is not interesting to them, then they'll think to themselves, yeah, why should I put resources in supervising this topic? So yeah, it's not, it is possible in some cases to do these kinds of cooperations, but yeah, it's not guaranteed in a way. So the question is if it's possible to write a thesis in cooperation with another department, and yes, that is possible, although the department, you have to have someone supervising the thesis who is also a member of the computer science department. So some professors are members of multiple departments, and if they have a membership of the computer science department, you're fine. Otherwise, you'll have to have someone from the computer science department co-supervising the thesis. Yeah.
In the web, you find the list with all professors from informatics, and you can look if it's there, then it's mostly possible that you can write with him a thesis.
Okay. Any other questions from the stream? Any questions in person? Maybe we just do some quick talking with Jannis regarding PhDs. Well, I hope some of you may be interested in pursuing a PhD later, and maybe you could just walk us through the process of what got you to start a PhD and, well, how you got into it, so the application process.
So if you're interested in doing or starting a PhD, you should ask yourself if you want to do a PhD in Germany or if you want to do a PhD, for example, in the US. Because if you want to do a PhD in the US, you have basically to start now with your planning, since the PhDs in the US often require some additional tests like GPA or some stuff like this. And it's much harder to get into a PhD in the US, since you basically have to fight for it a lot. Since, and that's the problem, if you want to go to a good university, especially in the US, they will require you to have some published papers. But in Germany, it's quite uncommon for you to already publish within your studies. Your first paper is most likely maybe your thesis or stuff like this, but it's not as common as in, for example, the US to publish already, which makes it hard for you to get in. In Germany, it's much easier to get into a position. What you have to do basically is to write your thesis, finish your master, and then while doing so, you can already submit or ask professors if they are interested in supervising a PhD, if they have the space and the money to have another PhD student. For me, it was basically I finished my thesis here, and while finishing the thesis, I submitted some applications for multiple universities in Germany, but also in Zurich and in Copenhagen. And in the end, I got multiple offers and decided that the best offer would be to stay in Darmstadt to build up a new center together with my professor called Hessian AI as a new PhD in the Hessian AI program called 3AI, now RAI. And I decided to stay here to keep my social circle and stuff like this. In my opinion, you should think about what you want to do after your thesis, because if you want to do a PhD and tell that to the professors, they are much more motivated to support you in your decisions, to supervise the thesis, because in the end, they may want to write a paper out of it. And if you say you want to go to industry, badly said, they're not as interested. But it's a decision you have to do for yourself. A PhD is a lot of work, and you should think about it. And especially in AI, going back 4 years, starting my PhD, I would do a lot of stuff differently. But yeah, I think that's everything for me now. If you have more questions about doing PhDs, please, yeah. What would I have done differently? Of course, the easy answer would be I would have known that LLMs will be the next thing to do in AI and have focused on large language models and stuff like this. No. The point is that doing a PhD in AI is hard nowadays because it's so fast, it's so much changing over time, and I would most likely have decided maybe not for an AI PhD, but more a specific PhD in, for example, natural language processing or stuff like this, instead of a general AI topic, which nowadays have a lot of, yeah, this is a nice paper, but have you tried LLMs? And this is very hard for me, but it's a personal decision. And of course, I would have planned more what I really want to do. I started in my PhD a little bit with, yeah, let's see what happens, what will happen. Not as organized as many of my colleagues, and that now bites me into my ass, so to say, because I think I did not have this plan which you could really need, or not need, but which helps you with doing your PhD. And I would have started earlier because I also got some rejections for my applications, of course. With, for example, yeah, you doesn't have a paper yet, or we need from you this and that, and you don't have that, or you need, or we require a specific certificate from you, and you don't have that, and stuff like this. So if I would do it again, I would start earlier, checking what I need for a PhD, for example, in the UK, as an example, and then check that. And I would go more directly to professors, say, I am interested in doing a PhD, because then, as I said before, they're much more interesting to help you with that and maybe share connections and stuff like this, which can really help or benefit you in your process.
Another question?
I would say, and that is not only for AI ML, it's for general, I personally can recommend practical labs and seminars. Why? It's quite easy. The practical labs and the seminars are in smaller groups. They are more direct within a group. For example, a seminar has 20 to 30 master students, and you will be supervised by a specific PhD. And this gives you connections, much easier than a lecture with over 300 students. Then that's the first point. The second point is practical labs are fun. And you should take as many of you as you can because they show you the practical applications of stuff like in AI. Not only learning the theory, but also implement a neural network, work with a neural network, stuff like this, which is often done theoretical in the lectures, but in the practical lab you actually have a hands-on experience with them, and that can help you with a thesis later, but also if you go into the industry. So my recommendation is choose as many practical labs as you can and want, as the same with seminars, to build connections and to have some fun, basically.
Okay, do you have any other questions from the stream? Okay, because then I would say we cut the stream and yeah, start with a few more delicate questions, if that's fine.
Hello. Okay, welcome to the closing. We're at the end of the Ophase. I hope you enjoyed. Yeah, so we collected some statistics, honestly only from the breakfast, but you know, I hope most of you came to breakfast and enjoyed the food. We used 12 whole meters of paper and 115 pairs of gloves. Maybe a little bit excessive, but at least we try to be clean, you know. We used 160 bread rolls and over 3 kilograms of bread on top of that as well. And here you see some nice little graphs, some coffee and juice usage. Unfortunate that they're both orange because I can't tell which one is which, but I think there was more coffee that was consumed. Yeah, and here's some of the spreads. Exactly. Okay. We would like some feedback, so if you have a minute, we would really like it if you could scan this QR code, and I think we will give you 5 minutes to fill it out now. I know, annoying, but it would be really nice and really helpful for the following years and so on, yes. Do you guys need more time, or are we almost done? I don't know. Okay, I think we'll just continue now. Okay. Yay. Okay, we'll wait like 30 seconds, a minute. We'll see. Okay. Was welche Slide als nächstes kommt? Achso, ja. Okay. Yeah. Okay, so I'm gonna keep going. So we've made this photo upload link. You can scan it and upload like your own pictures that you took of the Ophase if you would like to share them. And then we're gonna look through the pictures and filter out people with a red thing, you know. Yeah, a red lanyard. And then later you will get a download link. After we've done all that, you can then look through all the photos in like, hopefully like a couple of weeks when we're done. So if anyone would like to upload their pictures that they took to share with the others, then please do so.
The URL.
Yeah.
d120d/upload.
Exactly. Okay, thank you. I wanted to just mention the party again. I think it's going to be really good. We have a new location this time, and I think it's going to be like a lot better. And yeah, so please come tomorrow at 11. You can get a ticket at d120de/party, and it's like €1 cheaper if you buy it online. €2 cheaper. Yeah, it's also not expensive, and you can also just show up and pay cash. Yeah, or you can come to the help desk and pay cash there, and they will give you a ticket at the reduced price, so you don't have to use your credit card or pay online. It's fine. Yeah.
Please come. I think it's
Yes, please come. It's gonna be really good, actually. I think.
But it's better the more people come.
Yeah, exactly. If yeah, but I think we already have a lot of people coming. Yeah. Okay, now we're gonna say goodbye to the stream. So thank you for watching at home. I hope you also enjoy your time at TU Darmstadt when you arrive. Yeah, thank you very much. Bye bye.
you.